Welcome. My name is Zach Stone. Of course, I'm the internet's most popular instructor for the Power PE exam at electricalpereview.com. Excited to do this series every week for power systems for the FE exam. We've got a lot of great instructors, a lot of great tutors on our free review course for the FE exam at electricalfereview.com. I thought we'd have some fun. I thought it'd be more fitting if I taught the power subjects directly. So yeah, the format of this live webinar series, it'll be about an hour each week. I think we've got it scheduled for the next 5 weeks, alternating on Fridays and Thursdays. The recordings will be available. We'll be cutting the webinar segment into each subject. We'll be cutting it up into the recordings and we'll be putting them in the review course for the FE exam at www.electricalfereview.com. All right, so if you're new here, if you haven't met me in the past, again, my name is Zach Stone. I'm a professionally licensed engineer in the state of Florida. I've got an ABET accredited Bachelor's of Science in Electrical Engineering. I passed both the FE and the PE exam on my first try. All of my experience comes from the industrial world, hard hat, steel-toed boots, flame retardant clothing, all that great stuff, meters in hand, everything from, low voltage controls to power and lighting circuits 120 to 480 volt and medium voltage motors 2400 4160 all the way up to 69 kV substations. So a lot of hands-on experience, a lot of experience with project management, design, troubleshooting, you name it. Really enjoy the math behind electrical engineering. I think it's really interesting. And of course, I really like sharing that with others. And I've been primarily focused on helping electrical engineers pass primarily the P exam, but also the FE exam since 2014. You can find me on LinkedIn at ZA Stone. You can find me at our online class for the Power PE exam at electricalpereview.com. Of course, if you're tuning in here today, you're interested in the FE exam. You can also find me on our 100% free forever on-demand review course for the NCEES Electrical and Computer FE exam at www.electricalfereview.com. You can find me at ohmgurus.com. That's our new continuing education series. Once you have your license, we host 2 live continuing education seminars twice a month with different guest speakers. And you can also find me on our online community, www.powerpehelp.com. It's the most active online community for primarily focused on the P exam, but we have a lot of good discussions on the FE exam as well. All right, so here's the topics for the Power Systems webinar series for the FE exam. Today, we're going to start with complex power. We'll probably use every bit of the whole hour to get through this. This is mostly just the basics. And then in the following weeks, we'll be covering everything in the FE exam specifications and everything in the FE exam reference handbook, including balance and three-phase systems, wide delta connections, transformers, both single and three-phase and transformer connections. We're going to look at rotating machines, including the basics and the general formulas. We'll also be drilling deeper into synchronous and induction machines and DC machines. We'll have quick examples on servo motors and generators, just a couple of formulas on those in the reference handbook. We'll spend a lot of fun time here. Voltage regulation and voltage drop. We'll also look at power losses on transmission lines. A lot of this will apply to the PE exam after you take the FE exam. Then we'll look at lossless transmission lines. So today we're looking at complex power. This will take the whole hour. And then for the future weekly webinars coming up, we'll tackle these subjects one at a time. I'm going to go ahead and bring my calculator back here, and we're going to look at first the difference between sinusoids and phasors. Who knows the difference between these two? Well, sinusoidal signals, what we have here on the left, typically when we're working with power electronics, so when we work with sinusoidal signals, things like rectifiers, VFDs, AC to DC or DC to AC inverters, that's when we're looking at these sinusoidal signals. So for example, we could say the red signal on top, that could be our instantaneous voltage signal. Voltage with respect to time would be some maximum peak value, Vm, times sine omega t. We'll change this red to match. So here's our voltage signal in red. Here's the maximum voltage, also known as the peak voltage. That's going to be the highest point on the graph for V of t. And then next, in blue, would be our current. It would be current with respect to time. We can call this the periodic signal, instantaneous signal. Really, it's when we have that sinusoidal signal going from its peak to the zero crossing down to the negative peak and back in each period. So just like the voltage signal, this would be our current signal. We start with our maximum peak current value times sine omega t with any kind of phase shift, right? Maybe it's leading or lagging, or maybe they're perfectly in phase. Maybe it's unity power factor. Here is our current signal. And this peak right here would be I of M, which is, again, the maximum current, or sometimes we call it the peak current. All right, so everything on the left, that's our sinusoidal signals. They're signals moving and changing with respect to time. Over here on the right, this is a phasor diagram. This is how we can represent these quantities in phasors or complex numbers. So this is anytime we're really dealing with power applications, when we're dealing with RMS values instead of peak values. So over here on the right, this would be our complex current phasor. This would be our complex voltage phasor. So when we're dealing with phasors, right, instead of, periodic signals that are sinusoidal, when dealing with maximum or peak values, instead, if we're working in polar form, we're dealing with magnitudes and angles, right? If this was to be redrawn as a triangle, you can think of the magnitude as the hypotenuse of that triangle. That's the length, and the angle is the direction. And similarly, if we look at our complex voltage and polar, we're dealing with a magnitude and angle. And in this case, what's the angle of the voltage on this graph right here? What's the angle of the voltage as it's shown on this graph? Any guesses in the chat? We can see that the current is negative, right? This is theta I, but our voltage, voltage is at 0. You got it, Jason and Daniel. Voltage is directly at 0 degrees. How do we know? Well, the voltage phasor right here, that arrow, it's flat on the horizontal axis. It's right at 0 degrees. Now, when we're dealing with phasor quantities, when we're dealing with complex numbers, we typically don't say root mean square. We don't have to say RMS, but that's implied. But the RMS value is the magnitude. Anytime we're dealing with the magnitude of a complex number in polar form, that magnitude, that is the RMS value. All right, we're going to be doing examples today during this 1-hour webinar, looking at both the power electronics view in sinusoidal signals when we're dealing with peak and maximum values. We're also going to be doing some examples working with phasor quantities, looking at magnitude and angle. We'll also do some examples of it in rectangular form. We're looking at the real component, that horizontal leg of the triangle, and the imaginary component or the vertical leg. Careful, Daniel, that's not correct. Yeah, RMS, that is not a peak-to-peak value. Peak-to-peak value would be if we just took this peak value and multiplied it by 2, assuming a sinusoidal signal, but be careful. RMS is the magnitude that is not peak-to-peak. Be careful there. All right, so first off, let's talk about power factor. So in the reference handbook, we've got the formula for power factor, right? Power factor is going to be just the cosine of our power angle theta. And it's helpful to know that theta by itself, where does this angle come from, our power angle? We talk about this a lot in the PE class, but your power angle theta, it's always going to be the difference between two angles. Does anyone know what they are? It's theta something minus theta something else. Power angle theta by itself with no subscript, it's the difference, meaning we're going to subtract two angles. Anyone know what these two angles are? Theta something minus theta something else. We're always subtracting the voltage angle and the current angle. Power angle theta, it's always the angle of the voltage minus the angle of the current. And that's how we can tell if something's leading or lagging. We can look at the current angle with respect to the voltage angle. We're going to do that right now. So this first phasor diagram, what kind of power factor is this? Again, if you notice, the voltage is at an angle of 0 degrees. Is this a leading or lagging power factor? What do we think? When our voltage is at 0 and the angle of our current, theta I, is less than 0 degrees, it's negative when the voltage is at 0 degrees. Yeah, great job, Samuel and Jay. This is a lagging power factor. Again, notice the current angle is lagging the voltage angle. The current is behind the voltage angle. It's trying to follow. It's behind it. It's trying to catch up. Never quite reaches it. They're moving at the same speed, right? Same frequency. So if I have a lagging power factor, what kind of load do I have? Is this a resistor? Is this an inductor? Is this a capacitor? What kind of load? What's the only kind of load that will result in a lagging power factor? This is going to be an inductive load. You got it, Jay and Ben. This is an inductive load. All right, beneath this phasor diagram, we have a power triangle, right? We've got the real power is the horizontal or the real component. The reactive power Q, that's the vertical or imaginary component. Apparent power, S by itself, just the magnitude, that's the hypotenuse of this triangle. And then here's theta. Theta, of course, is the angle of our complex power, this angle, or this polar number right here. All right, is this a leading or lagging power triangle? If you're not sure, we can use process of elimination. We know that the phasor diagram on top is lagging because the current lags the voltage. We know this is the power triangle for this phasor diagram. So if this phasor diagram is lagging, then this power triangle also has to be what? This is a lagging power factor power triangle. What do you notice about the angle of our power angle theta for a lagging power triangle? It's always going to be what? It's always going to be greater than 0 degrees. It's always going to be positive. Always true for a lagging power triangle. Again, what kind of a load has a lagging power triangle? It's an inductive load. We can draw that out here. We can say this is either Jx of L, which is our inductive reactance. Of course, this is in the unit of ohms. Or maybe we're dealing with an inductor L in the unit of henries instead of ohms. All right, over here on the right, let's look at this set of phasor diagrams and power triangle. What's the angle of the voltage again? It's common to use 0 degrees for the voltage. How can we tell looking at it 0 degrees? Well, if I look at this red triangle, it's flat right on the horizontal axis. That's the 0 degree axis. All right, what's the current doing now? Is the current leading or lagging the voltage? Notice in this phasor diagram, the angle of the current, theta I, it's greater than 0 degrees. It's positive. Before, it was less than 0 degrees and it was negative. Now it's greater than 0 degrees when our voltage reference is at 0, which means our current angle is positive. Now it's, yeah, good job, kid. Now it's leading. Now we have a leading power factor. The current is leading the voltage. The current is in front of the voltage instead of behind. What's the only kind of load that can create a leading power factor? Maybe we're not sure. We can use process of elimination. We know it's not an inductive load, right? That was the previous example. An inductive load has to come from a inductive reactance. Now we're dealing with capacitive. Great job, Daniel, Chuck, Kate. You got it. Yeah, this is a capacitive load. Capacitive loads are responsible for leading power factor. So here's our capacitive load. I'm just going to draw a simple capacitor. And if we're working in the unit of ohms, we could say this is J operator times X of C, and it's negative. This is our capacitive reactance, again, unit of ohms. Or maybe we're dealing with capacitance in unit of farads. Same thing, different units. All right, let's look at the power triangle down below for this leading power factor. What stands out right away? What's different about this power triangle on the right that's leading compared to this power triangle on the left that's inductive? What's changed? Look at the angle, our power angle theta. Yeah, theta is negative, said Daniel. Now we can say theta is less than 0 degrees, which is the same thing as saying theta is negative. Real power P is still positive. It's pointing to the right, just like it was before, looking at this arrow here for the real power. What do you notice about the direction of Q, the reactive power, also known as the imaginary component of our complex power? Before, Q was positive, right? I look at this arrow right here. Q was pointing up. Now Q is pointing what? Q is pointing down. Now Q is negative. Before, Q was positive. What kind of power triangle is this? Well, we're drawing the power triangle for a leading power factor. This has to be a leading power triangle. Only concerned with the basics really of leading and lagging right now, comparing both the phasor diagram of the voltage and current with the power triangles below each of those phasor diagrams. All right, we've got lagging power factor on the left. We've got leading power factor on the right. There's one more type of power factor. Anyone know what it is? It's a special relationship. One more type of power factor. We can classify power factors either as leading, lagging, or, yeah, unity. Great job, Muhammad, Jay, and Chuck. Here is a unity power factor. What does unity mean? This is a power factor of what? This is a power factor of what? So here's our formula for power factor, right? Power factor equals cosine theta. Theta, the power angle, is the difference between which two angles? It's the difference between the voltage angle and the current angle. Always theta V minus theta I, always. All right, what's the angle of my voltage as shown right here? It's still what angle, just like it was in the other examples. It's still flat on the horizontal axis. So the angle of our voltage is 0, says Samuel. Yep. So I got some magnitude, 0 degrees. What's the angle of my current? We got some magnitude I in amps, 10 amps, 15 amps, who knows? What's my angle? The angle of the current is also, yeah, the angle is also 0 degrees. So what happens when I plug in 0 for my voltage angle minus 0 for my current angle? I'm going to have a power angle of 0 degrees, which gives me a power factor of what? Cosine of 0 is always what? Cosine 0 degrees? Always 1. Unity power factor means we have a power factor of 1. This is the definition of unity power factor. And notice in this example, both of our angles are 0. What if the angles were something else? What if my voltage angle was 15 degrees? If I have a unity power factor, what would the angle of my current be if my voltage was, say, 15 degrees? Any ideas in the chat? It'd also be 15 degrees. When we have a unity power factor, we can say that the current and the voltage are in phase with each other, which means whatever my voltage angle is will equal the current angle. So for here, we're keeping it simple. We're just using 0 degrees. They're both 0 degrees. 0 minus 0 is 0. Cosine of 0 is 1. Unity power factor. But for example, say the voltage angle was 15 degrees. The current angle would also have to be 15 degrees if power factor is unity because they're both in phase. They both have equal angles. In which case, what's our power factor? Well, instead of 0 minus 0, now I've got 15 degrees minus 15 degrees, and I still have 0 degrees for my power angle. Still have unity power factor. All right, what's the only type of load that can result in a unity power factor? Can't be an inductor, can't be a capacitor, right? Those were from previous examples of leading and lagging power factors. What's the only kind of load? Yeah, resistive. This is a resistive load. So here's what our load looks like. We've just got some resistor in unit of ohms. All right, look at our power triangle now. What do you notice about the power triangle for a unity power factor? Should look really odd, right? We're not really dealing with a triangle anymore, and now we've got a straight horizontal line. Yeah, there's no Q, said Samuel. So let's look at this. I like to draw a big triangle when we talk about unity power factor. Here's a right triangle. If we improve the power factor, we're decreasing the angle of theta, right? Here's theta, the angle of this triangle. So if we improve the power factor, if we get closer and finally equal unity, we equal power factor equals 1, that means we're decreasing the power angle theta to get theta to 0. What does that look like? That's like if I take this triangle, I keep everything the same, I'm just decreasing the angle until the angle equals 0. So now we've got a triangle with an angle of 0 degrees, which is really just a horizontal line. So a couple of good identities to know for your unity power factor power triangle. Theta is equal to 0, 0 degrees. And Q, I think, was it Samuel said that earlier in the chat, Q is also equal to 0. What do you notice about S, our apparent power, and P, real power? What happens when Q equals 0, theta equals 0, and we have a unity power factor? Yeah, they're equal. Good job, Samuel. Magnitude S equals P. The length on top equals the length on bottom. Again, just looking at the fundamentals here. All right, let's go ahead. Let's work some examples. Everyone got their calculator handy? First example says calculate the power factor for a circuit with a 30-degree power angle. So all we're doing is using this formula at the top. Let's try it. Power factor equals the cosine of our power angle. Power angle, according to the problem, is 30 degrees. What do we get for the power factor when I take the cosine of 30? Everyone get about 0.866. We'll round that to 0.87. I'm going to get the same value in their calculator. Now, important question. Is this leading or lagging? Is this leading or lagging? All we know is that the power angle theta equals 30 degrees. Is this leading or lagging? Lagging, says Chuck. Yeah. How do we know? This is a lagging 0.87 power factor. Was theta positive or negative? Theta was positive. It's greater than 0 degrees. This is true for a lagging power factor. All right, let's try the next example down here. Let's calculate the power factor for a circuit with, look at this, a negative 30-degree power angle. What's changed here? Instead of taking the cosine of 30, we're taking the cosine of negative 30. What happens in my calculator when I take the cosine of negative 30? I'm going to get the same what? I'm going to get the same 0.866 rounded to 0.87 power factor. So what's changed? I still have a power factor of 0.87. Is it still a lagging power factor? Ah, it's leading. Great job, Mohammed. Yeah, this is now an example of a leading power factor. How do we know the power factor is leading in this example? What was the giveaway? What was the clue? Before theta was 30 degrees, now theta is negative 30 degrees. So instead of theta being greater than 0, now theta is less than 0, right? Negative 30 degrees, which means instead of positive, theta is negative. This is only true for that leading power triangle, right? When Q is negative, it's pointing down, theta is negative. The whole triangle is pointing down. It's leading power factor. All right, let's try another example. This time we're going to complete the phasor diagram first. Example says in a single phase AC circuit, the voltage has a phase angle of how much? Voltage has a phase angle of 10, and the current has a phase angle of negative 35. Problem asks, what's the power factor of the circuit? So before I can use this formula, power factor equals cosine 30, cosine theta, cosine of power angle. First, we got to figure out what theta is. So remember, who can tell me in the chat, theta power angle, it's always the difference between what two angles? I've asked this a couple of times and I'm doing that because it's going to help for repetition. It's going to help for memorization. V minus I, great job, Allison. Yeah, it's always the angle of the voltage minus the angle of the current. You can't do it the other way. You can't say the angle of the current minus the angle of the voltage. You'll get the wrong polarity for your power angle. All right, so let's graph the phasor diagram first. Voltage has a phase angle of 10. So here's 0. I'm going to raise this about 10 degrees. Here's the magnitude of the voltage, whatever it is, and we have an angle of 10 degrees positive. We don't know what the magnitude is of the voltage, and we don't really care, right? We don't need it to calculate the power factor. All right, next, the current has a phase angle of negative 35, starting at 0, now going in the negative direction. That's about 30 degrees, and that's about 35. So here's our complex current, some magnitude I, don't know what it is, don't need to know for this example, but we know that the angle is negative 35 degrees. So let's find the power angle. We've got 10 degrees for the voltage minus negative 35 degrees for the current. Be really careful here. Look, we got two negatives. We got a double negative. This negative sign right here comes from taking the difference between the two angles to get our power angle, but it just so happens that the current angle is negative. So this is really what? 10 degrees minus negative 35. That's like adding them together. That's like 10 plus 35 degrees. That's going to be a power angle of 45 degrees. You can verify it in our calculator. 10 minus negative 35, same thing as 10 plus 35. We get a power angle of 45 degrees. We've got our power angle now. We're ready to find our power factor. Cosine of 45 degrees. That's going to give us a power factor of 0.707. I'm going to round that to 0.71. Everyone with me so far? Everyone get 0.71 in their calculator. We're rounding to 2 decimal places. Great. Good job, Samuel. Leading or lagging? Or could this be unity? What do we think? Is this a leading or lagging power factor? Lagging, says Samuel. Yeah, how do we know? Two different ways we can tell in this example. Number one, the easiest, well, my power angle, theta, is greater than 0 degrees. Theta is positive, right? Theta is positive 45. That tells me it's a lagging power factor. And the other is, look, my current right here is lagging my voltage. It's behind my voltage. Your phasors rotate counterclockwise. So if the voltage is here and the current is here, the current is behind the voltage. The current is lagging the voltage. This is the angle of our current from the 0 axis to the current phasor. We've got negative 35 degrees. but the angle from the current all the way up to the voltage, that's going to be our power angle, positive 45 degrees. All right, let's try it. One of the other formulas, we'll crank up the difficulty a little bit, and this time we're going to look at a sinusoidal signal. So here are your formulas in the reference handbook for real power P in the unit of watts. Real power P equals 1/2 times Vmax times Imax times cosine theta, if we're dealing with maximum values and sinusoidal signals, or real power P equals VRMS times IRMS times cosine theta, if we're dealing with phasors, if we're dealing with complex numbers. Let's read the example. We'll figure out which of these two formulas to use together. We'll add any information we can to this graph, and then we'll solve. So this example says a single phase AC load is supplied with a, look at that, maximum voltage of 169.7 volts, and it draws a maximum current of 14.2 amps. If the power factor is 0.8 lagging, what is the real power P delivered to the load? All right, maximum voltage, maximum current. Are we dealing with phasor diagrams, phasor numbers, RMS values, or are we dealing with sinusoidal signals, sine functions, maximum peak values? We're dealing with what? Yeah, we're dealing with sinusoidal, says Samuel. So out of these two formulas, am I going to use the one on the bottom that uses RMS values, same thing as magnitudes of phasors, or am I going to use the top version of the formula that has the maximum values, also known as peak values? Yeah, we're going to use the top version of the formula that uses sinusoidal values. All right, voltage has a maximum voltage of 169.7. That's this peak right here. This is VM, is 169.7 volts. I'm going to make that red just to match the graph. This is also known as a peak value, right? VM stands for V maximum, same thing as calling it the peak voltage. It's the highest point on the sinusoidal graph. All right, we'll do the same for current. This peak right here, it's going to be IM. Maximum current was 14.2 amps. All right, let's solve using this formula right here. I've got 1/2 times V maximum or VM or V peak. That's right here, 169.7 volts, straight from the problem, times I maximum, 14.2 amps. That's this peak right here, times 0.8 lagging power factor. Do I need to take the inverse cosine of my power factor to get theta and then take the cosine of theta? Or is there a faster way? What is cosine theta equal to? Well, cosine theta, that's the power factor. So no need to take the inverse cosine of our 0.8 lagging power factor to then just go right back to taking the cosine of it. I'm just going to plug in 0.80 for my power factor. Make sense? All right, so in the calculator, I'm going to type it in just exactly how it appears on my page. I've got 1 divided by 2 times VM, 169.7 volts. That's our peak voltage, also known as our maximum voltage, times 14.2 amps. That's IM, maximum current or the peak current, times my 0.80 power factor. All right, what's the real power? Calculator says 963.896 watts. I'm going to round that to the nearest watts just to keep it simple. We have 964 watts. Does everyone get that same value in their calculator for the real power P? Next question I have too is, if I had a leading power factor instead of lagging, but everything else stayed the same, would I still have 964 watts of real power? Good. Samuel said getting the same answer. So if I change 0.8 lagging to 0.8 leading, would that have changed my answer and my formula? Would I still get 964 watts if I had a leading 0.8 power factor? Same value. Notice leading versus lagging doesn't affect this formula. We're going to plug in our power factor right here for cosine theta. Doesn't matter if it's leading or lagging. Remember, that's just going to change, is the power triangle pointing up or is the power triangle pointing down? Still have the same horizontal real component, still have the same value of P. So that would be no change. All right, let's look at next page, same set of formulas. We're going to read the question and see if we're going to use the same one as before on top, or maybe we're using this bottom one. Example says a single phase AC load is supplied with 277 volts RMS and draws 12 amps of current. If the power angle is negative 15 degrees, what's the real power delivered to the load? Are we dealing with sinusoidal values like we were before, peak or maximum, or are we dealing with complex phasors? Are we dealing with RMS or magnitudes and angles? This time we're dealing with phasors, said Chuck. So we're going to use this formula for real power. All right, let's see if we can draw anything to conceptualize this information. We got 277 volts RMS for the voltage. We don't have a voltage angle, but we do have the power angle. So I'm going to go ahead and put the voltage at 0 degrees. So 277 volts RMS, that's the same thing as a 277 volt magnitude. And I'm going to arbitrarily use 0 degrees for the voltage. Question, is the power angle positive or negative? Theta is what? Theta is less than 0 degrees. Theta is negative. Is this a leading or lagging power factor? Is this a leading or lagging power factor? Yeah, it's leading. Good job. This is a leading power factor, which means that the current leads the voltage. The current is going to be in front of the voltage. So if I have a leading power factor, I'm going to draw a blue current angle. If I have a leading power factor and my voltage is currently at 0 degrees flat on the horizontal axis, is the current phasor going to be negative below the voltage, or is the current phasor going to be above and positive above the voltage for a leading? Good job, Greg. Good job, Chuck. Good job, Gid. Yeah, it's going to be above. It's going to be leading the voltage. So if the power angle is negative 15 degrees, and I'm using 0 degrees for voltage, what's the current angle going to be? I know we've got 12 amps of current. I'm going to have an angle of positive 15. Good job, Samuel and Greg. Yeah, here's 15 degrees for the current. Now, one more thing before we start solving. Notice the problem spells out root mean square RMS, also known as the effective voltage. That tells us we're not dealing with maximum voltage. We're dealing with RMS voltage. We're dealing with phasors. We're dealing with magnitudes. Notice it didn't say anything about the current. The problem didn't say 12 amps of peak current, 12 amps of maximum current. It also didn't say 12 amps RMS current, 12 amps effective current. How do we know if this is a peak value, also known as a maximum value for current, or how do we know it's RMS? I'm using it here as my magnitude of current. I'm using it as an RMS value. How do I know? Well, we got to assume, right? We're given the voltage in RMS. Problem doesn't say anything else, no more clues for the current. So it's up to me to assume, hey, if we're talking about root mean square voltage, effective voltage, RMS voltage, and they didn't specify about the current, I'm going to assume that the current is also RMS. The current is also effective. So that's going to be my magnitude for my current, 12 amps. 12 amps RMS. All right, plugging in our formula. We've got the root mean square of the voltage. That's the voltage magnitude, 277 volts given to us in the problem. RMS of the current, that's 12 amps, just like we just got done talking about, times cosine of the power angle. Power angle is negative 15 degrees. What do we get for the real power? What does the calculator say when I take 277 volts, multiply it with 12 amps, multiply by cosine of negative 15 degrees? We get about 3,210.7 watts. I'm going to round that to the nearest watt. I'm going to say that's about 3,211 watts. Or I could even say 3.2 kW, 3.2 kilowatts, same thing. Everybody get the same value in their calculator. Good job, Greg. Good job, Samuel. Good job, Daniel. Great. All right, let's try the next example. For the next example, it's the same values as before. So I'm just going to copy and paste what we already did. But this time, instead of solving for real power P, we're solving for reactive power. Problem says a single phase AC load supplied with, here's the same maximum voltage of 169.7 volts, just like we did previously, VM, draws a maximum current of 14.2 amps. Here spelling out this is a 14.2 amp maximum or peak current value. If the power factor is 0.8 lagging, what's the reactive power delivered to the load? Here's our formulas for reactive power in the reference handbook, very similar to real power. First of all, are we dealing with sinusoidal values or phasor values when we're given the maximum voltage and maximum current? These are sinusoidal. Good job, Samuel. So out of these two formulas, I'm not going to use the formulas with RMS. That's a phasor value. I'm going to use the formula on top with the maximum value because we're working with sinusoidal values. All right, what do you notice about the difference for reactive power? Reactive power formula, Q, compared to the real power, P formula. There's only one difference. Sine theta, you got it, Samuel. Yeah, instead of cosine theta, which is our power factor, we have sine theta. That's the only difference. All right, let's try it. Q equals, we're using the formula on the top because we're working with sinusoidal values. 1/2 times V maximum, 169.7 volts, times I maximum, 14.2 amps. Now I got to do what? Power factor is equal to cosine theta. We're dealing with sine theta. Now we got to figure out what's our power angle theta from our lagging power factor. So all we're going to do is take the inverse cosine of our power factor, inverse cosine of 0.80. What do we get for the power angle theta? What's the inverse cosine of 0.8? Does everybody get about 36.9 degrees in their calculator? Now, is theta positive or negative? Am I leaving theta positive just because my calculator says it's positive? Or is theta positive for a different reason entirely? Theta is positive why? Who can tell me in the chat? Theta is positive because our power factor is what? Power factor is, yeah, power factor is lagging. Good job, Chuck, Daniel, Samuel. Theta is a lagging power factor, which means theta is greater than 0 degrees. Theta is positive. It's up to us to assign the angle for the power angle, and we take the inverse cosine of it. You lose that information when you take inverse cosine. There's no way to know if it's positive or negative. Got to look at, is it leading or is it lagging? I'll show you an example of that too coming up when we have to make it negative. All right, we've got theta. So back to our reactive power formula. Now we're just taking the sine of theta, sine of that 36.9 degree power angle, and this is positive because the power factor is lagging. All right, let's see what we get typing into my calculator, just like it appears on my page. 1 divided by 2, 169.7 volts. Fix that 8. 14.2 amps, that's our maximum current. And here I'm gonna do a little trick. I'm gonna say take the sign. I'm gonna go up. See how this is highlighted? I want all those decimals as much accuracy as possible. I'm gonna bring it down, press enter one more time. The reactive power delivered to the load is, I'm going to round it to the nearest whole unit. I'm going to say 200, excuse me, 700 rather, 723. What are the units of Q? Real power P was watts. Reactive or imaginary power Q is unit vars, stands for volt amps reactive. I mean, typically make it plural. All right, everyone gets 723 vars. Good job, Jid, Chuck. Great. All right, next example, we're going back to our phasor diagram. I'm just going to copy the same phasor diagram we already drew before. Same problem. So we are now on page 12, solving for reactive power. We have the same single phase AC load as before, supplied with 277 volts RMS. That's the magnitude of our complex voltage. Draws 12 amps of current. That's the magnitude of our complex current. And we talked about before, we can assume this is RMS. We can assume that's a magnitude because our voltage was given as RMS. We have our power angle of negative 15 degrees. What is the reactive power delivered to the load? Which of these two formulas am I going to use? I'm going to use the same formula before that used maximum values, peak values, or I use in the bottom formula that deals with phasors, right? We're dealing with RMS values. RMS values, that's the magnitude of my phasors. All right, let's try it. VRMS, that's 277 volts. Next, IRMS, that's 12 amps times the sine of theta. Don't forget that theta in this example is negative. All right, what do we get for the reactive power for this example? I've got 277 volts RMS, 12 amps RMS times sine of negative 15 degrees. All right, does everyone get negative 860 vars, just rounding to the nearest whole unit? Why did I get a negative sign here? Did my calculator make a mistake? Did I make a mistake? Why does my calculator give me a negative value for the reactive power? Is theta positive or negative? Theta is less than 0 degrees. Theta is negative. Is this leading or lagging power factor? This is a leading power factor. If I were to draw a power triangle, here's the base. Here's real power P. Is Q going to be positive pointing up, or is Q going to be negative pointing down? Yeah, Q's negative pointing down. Here's our leading power triangle. Look, here's the angle of theta. Notice that theta is less than 0 degrees. Theta is negative. Pretty neat. All right, coming up, let's see. We're doing pretty good on time. We'll probably go about 15 minutes over. Next, we're going to look at the formula for complex power. Formula for complex power in the reference handbook. S equals V times I conjugate, also equals P plus JQ. It's really important to get in the habit of using proper notation now. This will really help when you get to the PE exam. But I just want to point out the reference handbook, they use bold to indicate complex numbers, to differentiate from just the magnitude of a complex number. So this formula, get in the habit of writing complex S, complex power equals the product, multiplication, of the complex voltage and the conjugate of the complex current. These are complex numbers. This is the real component. This is the imaginary component. By itself, it's not a complex number. It's also helpful to note that this version of the formula, this is for single phase circuits, single phase power only. When we get into balanced three-phase systems on the next webinar, we'll look at the three-phase version of this formula. The reference handbook doesn't tell you, so I just want to point out this is just for single phase. All right, so what do we got here? This formula is also equal to P plus JQ. P is the real component, right? If this arrow is complex power, P is the horizontal, the real component of our complex power. Q is the imaginary component, also known as the vertical component. Again, here's our complex power, complex S. Here's Q. Q is the imaginary or vertical component of that triangle. This is rectangular form. We can also represent complex power in polar form as both magnitude and angle. So this is the magnitude of complex power. Again, the reference handbook doesn't do a good job of differentiating between magnitudes and complex numbers, so I'm always going to try to point that out to you. Here's really the magnitude of our complex power, also known as just apparent power. And apparent power is magnitude only. Complex power is magnitude and angle, or real and imaginary component. All right, and last here is the angle. There's our triangle angle. Again, this is complex power represented in rectangular format, P plus JQ. This is complex power represented in polar format, magnitude and angle. So in the reference handbook, they include the power triangle with these formulas. P equals VI cosine theta, Q equals VI sine theta, S equals just VI. So apparent power by itself, right? I can get rid of these complex numbers, just use magnitudes, which means I'm also just going to get the magnitude of S. How about this formula, P equals VI cosine theta? Look, this is the same as the formulas we were just using. This is the same as VRMS times IRMS times cosine theta or times power factor. Same thing for reactive power. This is the same thing as VRMS IRMS times sine theta, right? These are your magnitude values, same thing as your RMS values. So don't get confused where they show it with the power triangle in the reference handbook. They don't say RMS. It's implied. It's the same thing. All right, phasors with complex numbers. Let's talk about this conjugate. Complex current conjugate used in the formula for complex power. What does this conjugate do? No change to the magnitude. What do I do to the angle of my complex current to apply the conjugate? All we're doing is changing the polarity. If the angle was positive, now the angle's negative. If the angle was negative, now the angle is positive. All the conjugate does is just change the polarity. All right, let's try our first complex power example coming up on the next page. Get your calculator handy. You can help me verify the answer. So same formulas we just looked at. Problem says a single phase AC load is supplied with 240 volts at 0 degrees, draws a current of 10 amps at negative 36 degrees. We want to know what is the complex power absorbed by the load. Which of these two formulas am I going to use? Do I have any information about the real and reactive power? Nope. I do know what? I do know my complex voltage and complex current. So we're going to use this in the middle. Let's fill out the phasor diagram. Let's see, the current is 10 amps, negative 36 degrees. Voltage is 240 volts at 0 degrees. All right, using this formula right here, remembering that these are complex numbers. So I'm going to say complex power equals, here's the complex voltage first, 240 volts at 0 degrees. Here's the current conjugate. So current by itself, 10 amps, negative 36 degrees, but we're going to have to apply the conjugate, and we'll do that in our calculator. All right, let's see. Clear the calculator. I've got 240 volts at an angle of 0. You could also just ignore the 0 angle in your calculator. It wouldn't make a difference. I'm just going to type it in the same way it appears to avoid mistakes. Times 10 amps. All right. The current has an angle of negative 36 degrees. How do I apply the conjugate in my calculator before I move forward? What do I got to do right here to my current angle? Current angle is negative 36. What is this asterisk? What does this conjugate do? Yeah, good job, Samuel. I'm just going to remove that negative sign. I'm going to make it positive. All right. In polar form, we have a complex power of 2,400 VA, also known as volt-amps, angle of 36 degrees, right? This is our complex power represented in polar form with both magnitude and angle. Or how do I convert this to rectangular form? Same information, but we're going to have it converted from polar to rectangular. Let me use my calculator. I'm going to go, so I like to keep my calculator on polar mode. I use it more often. You could change it to rectangular, but an easier way to do that is I'm going to go into my second complex menu. I'm going to scroll down to number 5. Number 5 says A plus BI. That tells the calculator, hey, that last answer, 2400 volt amps at 36 degrees, convert it for me to rectangular. So in rectangular format, our complex power is, let's see, 1,000. See how easy that is? 1,942 watts. There's our P plus the J operator times Q. See this arrow sign right here in my calculator? That just tells me, hey, you got to scroll over. You got to hit this arrow sign. So here's our reactive power, 1,411 bars. This is rectangular form. Complex power equals P plus J times Q. Both are correct. In this example, I didn't specify what format to put it in. That way we could put it in both and talk about it. Now, electrical engineering, we typically put our J operator in front of the imaginary component. Look at my calculator. That J operator, the calculator just shows it at the very end, and calculator, of course, uses I instead of J. Same thing. All right, pretty neat. Let's look at same problem, but we're going to look at just the real power on the next page. We're on page 15. This is the same problem, same values. Now the problem asks, what's the real power P absorbed by the load? Which of these two formulas do I want to use? I want to use the formula on the right. So in our calculator, that last answer that we got in rectangular form was 1,942 watts plus J times 1,411 vars. Which of these is the real power absorbed by the load? Look, this quantity is the real component. That's our real power P. This quantity is the imaginary component. That's Q. So we already have the information to solve this problem. 1,942 watts are absorbed by the load. And see if we can verify it this way too. P equals VRMS times IRMS times cosine theta. P equals, V was 240 volts times the current, 10 amps, times cosine theta. What's the power angle here? My voltage is at 0 degrees. The current is at negative 36 degrees. Voltage angle 0 minus current angle negative 36. That's going to be what? Yeah, positive 36 degrees. All right, we should have the same value. Let's try it. 240 times 10 times the cosine of 36 degrees. We get the same 1,942 watts. When we multiply by cosine theta, it just converts, but this is the magnitude, right? V times I. When we multiply by cosine theta, it converts this to the real component. And when we multiply by sine theta, it converts this to the imaginary component. That's all cosine and sine are doing. It's just a little bit of trig. All right, next problem coming up. We're going to look at same problem. This time we want to know if we can calculate the reactive power absorbed by the load. All right, same problem. We want to know what's the reactive power Q absorbed by the load? How much is this equal to, right? Let's see, before we had the real power. Now we're going to figure out the reactive power. Did I already do all the work in my calculator on that last example when we converted? Here's our complex power in polar. Here's our complex power in rectangular. Here's the answer in my calculator. Do I already know the reactive power? How do I find Q? Well, if I can represent the complex power in rectangular form, then Q is just the imaginary component. Q is 1,411 vars. Let's verify it using this formula right here. Q equals V times I, 240 volts times 10 amps. This time we're using sine for Q, sine of the 36-degree power angle. All I'm doing, I'm just changing cosine to sine in my calculator. That's all. Look at that. We get the same 1,411 vars. Again, sine theta, it's just converting to the reactive imaginary component. All right, everybody with me so far? It's really important to understand the different values of the power triangle. Now we're going to look at the apparent power. So same problem as before, but this time I'm going to go back. We already have this information in our calculator in polar form. Again, all the same values. Let's see. Actually, you know what? Nope, I'm sorry. This is a different problem. Great. All right, scratch that. Different problem. We've got a single phase circuit has a real power of 1.5 kilowatts and a reactive power of 500 vars. Problem asks, what is apparent power S? Where's apparent power S located on my power triangle? You can tell me in the chat. So here they're giving us directly P equals 1.5 kW, Q equals 500 var. They want to know what's the apparent power. Yeah, hypotenuse. Good job, Samuel and Chuck. Here's the hypotenuse right here. Here's magnitude S equals magnitude V times magnitude I. So you want to know what's this? So here's what I'm going to do. Look, we already know P and Q, right? I don't know voltage and current, so I can't use this formula, but I know P and Q. I can say, remember, these are really complex numbers. Complex power equals P plus Q. Complex power equals 1.5 kilowatts. There's my P plus J times Q, 500 vars. I'm going to plug this in my calculator. And since if I click on mode, R angle theta, that means my calculator is in polar mode. It means if I type in a complex number in any format, it's going to return it in polar. Well, I want to get it into polar form because that'll give me just my magnitude. So I'm going to leave it in the mode it's currently at. I'm typing 1.5 times e to the 3. There's my 1.5 kilowatts real power P plus J or I times 500 var. And again, this is rectangular format. When I press enter, the calculator is going to convert to polar format because that's the mode I have it set for. So this is rectangular. And here's polar. What's our magnitude? Looks like 1,581 volt amps. And that's a power angle of about 18.4. 18.43. Yeah, we'll round to 18.4. So what's the apparent power? Here's the apparent power right here. Apparent power is 1,581 volt amps. Again, apparent power is just the magnitude only of complex power. So our hypotenuse right here, this is equal to 1,581 volt amps. Here's our power angle theta, 18.4 degrees. And that's every aspect of the power triangle. We've got the real power P, reactive power Q, angle theta, magnitude S. Or we can represent complex power as 1,581 volt amps at our angle of 18.4 degrees, or 1.5 kW plus J times 500 bar. Same thing. All right, any questions on this? We've got one more example on complex power, and then a couple of examples left with special properties of resistors coming up. All right, let's take a look at next problem. This is going to be the same problem as before. So I'm going to copy all the same values we already drew on our power triangle. We've got P, we've got Q, we've got S, we've got theta. Same problem as before. Now the problem asks, what's the power factor? Interesting. So before we solved for the complex power in polar from the complex power given to us in rectangular. What's the easiest way to find the power factor? Let's go back to our power factor formula. Look, all I need to do is find my power angle theta, pick the cosine of that angle. There's my power factor. Which one of these two formats for complex power S, right? That's this complex number right here, S hat, in rectangular form on top or polar form on bottom. What's the easiest one to work with? Look, here's theta. I'm going to use polar form. I'm just going to take cosine of the angle of my complex power. Cosine theta, cosine 18.4 degrees. Here's a neat way to do this. Look, my calculator, I don't have 18.4. I just rounded to one decimal place. I've got 18.4349, et cetera, et cetera. If I want to be as accurate as possible, I'm going to go into the complex menu. I'm going to tell the calculator, give me just the polar angle of this last complex number. Boom, there's our 18.4 degree power angle with all the decimals. Now I can take the cosine of it to get the power factor. So we have a power factor of 0. I'm going to round that to two places, 0.95. All right, I'm going to ask, is this leading or lagging? How do we know? Anyone want to take a guess at that? Is this leading or lagging? Is theta positive or negative? 18.4 degrees, theta is positive. It's greater than 0 degrees. This must be a lagging power factor. All right, there's one more way we could have solved for power factor. Anyone know what it is? Who remembers back from trigonometry, who remembers SOHCAHTOA? SOHCAHTOA. This is just a mnemonic device that's helpful to remember the relationships with cosine, sine, and tangent. So power factor is the cosine of our power angle theta. So I'm going to look at this term in the middle, ka, right? S stands for sine, C stands for cosine, T stands for tangent, SOHCAHTOA. If you've never heard this before, it's just a mnemonic device they teach in school to remember your trig. So cosine of the angle of your triangle, cosine theta equals the adjacent leg of the triangle divided by the hypotenuse leg of the triangle. If I'm looking at my theta angle, which is the adjacent angle next to it? Here's my adjacent angle. Adjacent angle is real power P. And then which one's the hypotenuse? That's the easiest one, right? That's the big leg of the triangle. So the hypotenuse is the apparent power S. What is cosine theta equal to? Cosine theta equals power factor. So we can say power factor equals real power P divided by apparent power S. Let's see if we get the same value of 0.95. What's our real power? Real power is 1.5 kilowatts on top, 1.5 kW. Apparent power is how much? Got 1,581 volt amps. All right, let's see if we get the same value. Using rounded numbers in my calculator, I'm going to type in 1,500 divided by 1,581. Look at that. Same power factor. And again, we know it's lagging because theta is positive. Pretty cool. So we can calculate power factor using polar numbers, right? Just taking the cosine of the angle, or we can calculate power factor using the rectangular form, right? Using the real component P divided by the hypotenuse S. Both will give you the power factor. All right, getting close to the end, we got 3 more quick examples on special cases of resistors. These are formulas straight from the reference handbook that we're going to look at. Resistors have a unity power factor. What's my power angle equal when I have unity power factor? Good, Samuel, like it? This is our unity power factor, or power factor equals 1, theta equals 0 degrees. Can you tell that my current and voltage are both in phase with each other? They have the same angle. Here we got them both on the 0 degree axis just to make it easier. Now, what trig relationship exists when you have 0 degrees? What's the difference between P for my resistors compared to the general form for P we've been using so far, right? We've been doing VRMS, IRMS times what? Times cosine theta, right? This is times power factor. Why do we get rid of the cosine theta? Why do we get rid of power factor in this formula for resistors? What's cosine of 0 degrees when theta equals 0, when I have a unity power factor, when I have a resistor? Maybe you're not sure, you don't have it memorized. Use your calculator. What's cosine 0? Cosine 0 is just 1. So for resistors, if I'm calculating real power, I can just get rid of this term because this term equals 1. 1 times VRMS times IRMS equals just VRMS times IRMS. We also have 2 other formulas in the reference handbook related to this. These formulas we're going to use all the time when you get to the power exam, to the PE exam. They're very, very helpful. All right, let's try an example. Single phase resistive load. Okay, that tells me my power factor is unity, is connected to 120 volts RMS and draws 10 amps. So this is V equals 120 volts. I'm going to give it 0 degrees. I'm going to write my current down below so it fits. Complex current equals 10 amps. What's my angle of my current if it's a resistive load and I've already picked 0 degrees for my voltage? Resistive load, the current angle has to equal the voltage angle because they're in phase, because it's unity power factor, because power factor equals 1, because theta equals 0. So if I already picked 0 degrees for the voltage, then I've got 0 degrees for the current. I've got three formulas. P for resistor equals VRMS times IRMS. P equals VRMS squared divided by R. P equals I squared RMS times R. Which one of these three formulas are we going to use? I don't have any information about how big that resistive load is, R in ohms, but I got the voltage and I got the current. So I'm going to use this formula right here. VRMS is 120 volts. That's the voltage magnitude. Magnitude RMS, same thing. IRMS is 10 amps. Don't even need to use my calculator, right? 10 times 120. We're just going to add an extra 0 right here. We get 1200 watts. Easy enough. All right, let's try the next example. We'll see which formula we're going to use. Next example says a heating element is powered by 240 volts RMS, has a resistance of 48 ohms. What's the real power? So we're looking for what's the real power? See if I can get a square here. There we go. We've got a 48 ohm heating element and 240 volts applied. Which formula am I going to use? I don't know the current. I can't use this one. I know the resistance, 48 ohms, but I don't know the current, so I can't use the one on the right. I got to use the one in the middle. We're going to square the voltage, divide by the resistance. 240 volts RMS squared divided by the 48 ohm heating element. How much real power does that heating element, that 48 ohm heating element, consume when we supply it with 240 volts? All we're doing is we're squaring the voltage, we're dividing by the resistance. We're going to use these formulas all the time when we get to the PE exam. All right, we've got 1200 watts. Once again, different problem from the previous example. It's just a coincidence that they're the same. All right, last example for the day, last example for the webinar, last example for our first seminar on power systems for the FE exam. Ready? A device draws 8 amps RMS. It has a resistance of 10 ohms. What's the real power? So this time the resistance is 10 ohms and the current drawn by it is 8 amps. Solving for real power P, I don't know the voltage. I can't use this formula. I know the resistance, still don't know the voltage, can't use that formula. We're going to use the formula on the far right. This time we're squaring the current, 8 amps RMS squared times the resistance of 10 ohms. All right, who can tell me in the chat, last problem, how much real power does this 10 ohm resistor consume if it's drawing 8 amps? What's 8 amps squared times 10? Let's see, I'm seeing 640 watts from Samuel, Chuck, Oscar, Robert, Gid. Great job. Let's see. There it is. That resistor is consuming 640 watts. All right. Excellent job, everybody. We went about 20 minutes over, so I won't keep you any longer than I need to. Once again, all of the recordings for this live Power Systems webinar series, we're going to cut them up. We'll put them in the free FE review course. We'll send out emails when you do or when we do so you don't miss it. Check the schedule. I believe the next week's is on Friday. Then I believe we have 2 Thursdays in a row, and then I believe we're back to Friday. So check the webinar page and make sure you're signed up for all of them. Certainly hope you enjoyed it. Let's see, Ben said, thanks, great webinar, much appreciated. Good. Samuel said, appreciate the time. This has been helpful. Great. Ryan said, thank you, Zach. Great course webinar. Great. 1 to 5, how comfortable do you feel with these formulas after we've gone through these examples together? 5 being the best, 1 being the poorest. Let me know in the chat. Good. I'm seeing 4s, 4.5s, and 5s. Wonderful. Yeah, Chris, I'll probably make the slides available in the future once we're done. All right, everybody. Hope you enjoyed. Let's see. Next week, we're going to be doing balanced three-phase systems, looking at Y and delta connections. And yeah, we'll take this 1 week at a time, get you prepped for power systems. I'm going to teach you everything you need to pass the FE exam for complex power and power systems. All right, everyone. See you next week.